Hi everyone, welcome back to the class. And continuing from the lecture slide, I wish to provide you two Python demo. One for the CO2 transportation in the pipeline, and the second one is the CO2 flow in the porous media or rock sample. Let me get it started. Please open the iClass, and from the iClass, you can find the Python demo for the CO2 flow in the pipe and then porous media. And if you open this folder, you can download all these three Python files. The first one is about the equation of state of CO2, and the second and the third Jupyter Notebook file are for the one for the pipeline, and the second one for the porous media. And they are located in the 7th week from the iClass. And please let me know if you have any issue in downloading these three files. So I downloaded these three files and then move it to this working directory. And from here, I will open my Anaconda. So from here, I will open my Jupyter Notebook. So and by the way, please note that we have two different assignments. The first assignment is due this next. So the first assignment is due this Thursday. So no, actually this Saturday. And this assignment, by using the previous Python demo, please provide a viscosity and the density of the CO2 with a given condition. And after you get the value, you have to take the snapshot of your Python run and then provide your snapshot to the iClass. And for the answer, you are supposed to submit it from this Google form. So you can submit the answer from the Google form, but please don't forget to submit your PDF snapshot of your Python run. Now we have our two demo here. So first, please open the flow in the pipe updated Jupyter Notebook. And here we have explanation of the problem. So we have carbon capture location from some facility or the factory or the power plant. And from the carbon capture location, we have to transport the CO2 to the carbon storage location. Typically in South Korea, it will be the offshore. And between these two, we have a pipeline whose total length is 50 kilometers. And we also have a specification of the pipe. The diameter is 0.35 meter, and the relative roughness in the pipe, inside of the pipe, is 10 to the minus 5 meter. And in the inlet condition, so we had 10 megapascal, and then so the temperature was about 25 Celsius. And the question is, what will be the outlet condition, the pressure that we will have right before we inject the CO2 into the subsurface? And then, and also in this particular transportation, we assume the isothermal condition, so the pressure and the temperature is same throughout the pipeline. And the feeding rate of the CO2 into this pipeline is equal to the 12,000 tons per day. So this is it. So if we briefly summarize the sequence to get the pressure loss in the pipeline, so first of all, we have to define or the required variables such as the v, the average velocity, or the mu, which is the viscosity, and also the diameter and the length, and also Reynolds number, and so on. So once we have the Reynolds number, then we have to tell whether it's laminar or turbulent. And based on their flow pattern, if it's laminar, then now we have to calculate the friction factor. And in case of the laminar, it will be equal to the 64 over RE if laminar. And if it's not, then turbulent. So if it's turbulent, then we have to read it from the Moody's chart. But instead of reading the Moody's chart, we are going to use this empirical equations that we have in this Python demo. And once we have this friction vector, then now we have to calculate dP over dL, the pressure loss per the unit length of the pipe, which is equal to here. So the F times rho over 2 times V square over diameter of the pipe. And once we have this, then now we can calculate the pressure losses. So the total pressure loss is equal to dP over dL times the total length, right? And this is how we can get the P2 is equal to P1 minus delta P. So this is the entire process of how we can get the pressure from the outlet or in this CO2 transportation. So for this, we have a we are going to continue to use the viscosity and the density function from the CO2 underscore EOS function, and we review it from the last Python demo. And on top of this, we are going to have this function. So we have some explanation here, but this is not necessary. And if you remove this, this is very simple. Once we provide a mass flow rate and the density of the fluid, the mass flow rate divided by the density will be volumetric flow rate, right? So, and here we have an explanation of individual input, but it's very simple. And also for the velocity, if we divide the diameter of the pipe and volumetric flow rate, then volumetric flow rate divided by the cross-sectional area, then there will be average velocity. And the Reynolds number, it's a rho Vd over viscosity. So this is Reynolds number. And then for the friction vector, in case the given Reynolds number is less than 2,100, which is laminar flow, then the F is going to be calculated in this way. And if it's not, then we have to read it from the Moody's chart. But instead of using the Moody's chart, we are going to use the empirical equations so that we can get the F directly. And in case the Reynolds number is lower than 4,000 and larger than 2,100, then it's going to be the intermediate or the critical region. So in that particular case, we do not have we do not know what the friction factor should be. So in this case, we are going to make the error. So basically, this function is to calculate the friction factor. And once we have friction factor, following the Darcy-Weisbach equation, we are going to calculate the delta P per L, which is this. And here we have equation. So we run it. So once we run and define these functions, then we can use this function later on. And so the P1, which is the inlet pressure here. So P1 means this is where P1 and the P2 will be here. And then also, of course, the temperature will be the same, but I'm gonna just say P1 and P2, and P1 and P2 gonna be the same, which is 25 Celsius. So first, we have to define the required variable in this demo. So P1 is 10 times 10 to the 6 Pascal, and then T1 Celsius, but now we have to convert it into the Kelvin absolute temperature, the diameter, and then the lengths are given here in the meter. So as we are gonna use everything in the SI unit, and the roughness 10 to the minus 5 meter, and then so mass flow rate, it was 12,000 ton per day, but I wish to convert it to the kilogram per second. So we defined the required variable, and then we have to get a density and the viscosity at the inlet of the pipeline, and for that we are going to use these. We are going to use the density of the CO2 and the viscosity of the CO2 function. But as we covered last time, the equation only takes the pressure in bar, so we have to convert the P Pascal to the bar, and the conversion is simply divided by 10 to the 5. So P1 in bar is equal to the P1 divided by 10 to the 5. So, and then we are providing this pressure here and there, and then the temperature is in the Kelvin, so it's absolute temperature, so we can directly provide a T1s here, and that's how we will get the rho mu, and this mu is in the centipoise by the definition of this function. But when we get the Reynolds number, every unit should be in SI unit, so mu will be converted to the Pascal second. So to convert the centipoise to the Pascal second, we have to multiply by 10 to the minus 3. So mu, this one is in the Pascal second, and this one was in the Pascal centipoise. So from there, we have a mass flow rate and then the density. So by dividing the mass flow rate by the density, we will have a Q1, which is the flow rate. And then also from the flow rate and the diameter of the pipe, we can also get the average velocity. So if you run it, then we have a density around 810, viscosity around here, and the flow rate 0.171 cubic meter per second, and the velocity is about 1.781 meter per second. And then we need to calculate the Reynolds number, friction factor, and also pressure loss per length. So we calculate the Reynolds number by providing the rho, v, and diameter, and the mu. So that's going to be the Reynolds number. And the friction factor will be calculated by giving the roughness as well as I just found an error. Sorry. So roughness is 10 to the minus 5 meter, but the relative roughness should be rough divided by d. So that will be relative roughness, which is dimensionless, right? And as far as I know, it's friction factor. So yeah, the first input should be relative roughness, not the absolute roughness. So we have to get the relative roughness here in the very first step. This is same, and then in the third step, we have to provide the relative roughness, not the absolute roughness. So we just named it in this variable name. So we provide this, the Reynolds number, and that's how we get the F, and the F density V1 and D, there will be the del P per L, and this is how we got the Reynolds number is way larger than 4,000, and then friction factor is about 0.01122, and in that case, the pressure loss per 1 meter length of the pipe is going to be 41.2 Pascal per meter. So we are losing 41 Pascal every 1 meter of the pipe transportation. And by multiplying that variable by the total length of the pipe, then we can have a total pressure loss, and P2 is equal to P1 minus that pressure loss. And if we get the how much is it, then we are going to lose about 2 megapascal pressure over the 50 kilometer of the pipe length. And in that case, the pressure in the outlet will be about 79.39 megapascal. And this is the demo. And lastly, if we recalculate the viscosity and the density in the outlet, and if we compare them into the inlet viscosity and the density, this is what we got. So from the inlet, because we have a different pressure, we had this density and this viscosity, but that viscosity and density will be changing to 744 kilogram per cubic meter and 0.041 centipoise. So the viscosity is very significantly reduced, and also the density is also changing. So which means for now we get the pressure as this, but this pressure may not be correct because the density and the viscosity we used in this particular demo is not going to be representative throughout the entire pipeline. So we are not covering this yet, but as a one further discussion, we may need to consider how to improve the accuracy in this demo, because this inlet pressure is not going to be the representative. So how can we recalculate this to get a better or the more accurate pressure losses throughout the pipeline transportation? So this is going to be our future work, but I will stop for now. And this is for the pipeline transportation. And in the second Python demo, we have CO2 flow in the porous media. So here, in this demo, we have three different questions. So first question, and then second task, and the last task. And then for the last task, I didn't provide any answer yet. And this will be the assignment for that is due in 2 weeks. So please review the lecture note and then follow the sequence to get the answer. And then once you get the answer, please summarize everything into the 2-page of the PDF file and then submit it to the iClass. So in the first task, we have this core sample, and we have an inlet pressure of 5,801.5 psi, and the outlet is 5,775.5 psi, and the CO2 is injecting from the left to the right, and this core is fully saturated by the CO2. So we just assume that it's fully saturated by the CO2. And the length is 6 inch, and the diameter is 1 inch. And then we have to use this Darcy's equation. And for this, we are going to use the EOS function, the same as the previous demo. And first step is we have to define the required variable. The required variable is permeability, temperature, diameter, length, P1 and P2. And P1 and P2 are given in PSI. So we have their name for the variable and then their corresponding units. And the del P, which is the pressure difference, is P1 minus P2 in PSI. And the area of the flow, which can be calculated from the diameter of the core sample. This is basically d to the 2 divided by 4 times pi. So this is the area. In the second step, now we have to calculate the viscosity of the CO2, because viscosity is not given, so we have to get a viscosity. And P1 and P2 are given in the PSI, but again, to use this viscosity function, we have to use the Pascal, the pressure in the bar. So P1 in bar and P2 in bar is the conversion of P1 and P2 into bar unit. So this is conversion equation, and this is another conversion equation. And this is how we can get the mu1 and mu2. So inlet viscosity and the outlet viscosity, and inlet viscosity is here, measured here, and the outlet viscosity is measured here. So to get a one representative viscosity throughout this pore network, we are gonna simply get a mean between these two inlet and outlet permeability viscosity. So the mu underscore CO2, which is average viscosity between the inlet and the outlet, this will be 0.09017 centipoise. And then we can use the Darcy's equation. Darcy's equation is Q flow rate is equal to conversion factor, permeability area divided by the mu and del P over L. And this is the outcome. So in this case, the flow rate of CO2 will be 0.53171 better per day. In the second task, it's everything is the same. So we have the same inlet pressure and the outlet pressure, and then the only difference here is now we have more than one phase into this core sample. So we have a 40% of the CO2 and the 60% of the brine, and the question is compute the CO2 and the brine flow rate. And the relative permeability curve are given or provided here. So as now we have 60% of the brine, and this relative permeability curve is given by the water saturation. So in the lecture note, we had a CO2 saturation, but now we have a water saturation. So we have to use the water saturation, which is 60%. So if you read the 60% of relative permeability curve, and there will be around 0.1 for brine, and also if it's 0.6, then it's about 0.3 for CO2. So relative permeability of the CO2 will be 0.3, and the relative permeability of brine will be 0.1. So that's what we can have from this relative permeability curve. So everything just same as before. So I will just skip it, and then on top of the Darcy's equation, we have to provide this relative permeability. The CO2 relative permeability is 0.3, and that's why we provided 0.3, and that's how we can get this. So yeah, the CO2 flow rate in this case will be this. So even in the same condition, due to the multi-phase, the flow rate of CO2 will be much less than what we had in the previous case. And then lastly, we have an example of the CO2 injection. So this is for the offshore CO2 storage. So we have a sea level and the offshore platform, and then the sea floor, and then below the sea floor we have this red injection well, and we are basically injecting this CO2 into the aquifer that are provided as this cylinder shape. And if we measure the pressure of the bottom hole, then there will be 5,500, and the aquifer, the boundary pressure will be 4,000, and then the average pressure will be 4,500 psi, and then this entire formation is assumed to be homogeneous, where the permeability is 150 millidarcy, and the thickness will be 30 feet, and then the radius of the formation will be 1,000, and also the radius of the wellbore will be 0.3 feet. And the temperature is given in Fahrenheit, so we have to convert this into the Kelvin so that we can reuse the viscosity and the density function that we had. And the question is, in this particular case, what will be the flow rate of the CO2 into this aquifer? So when we keep the pressure of BHP bottom hole pressure as 5,500 psi, then how fast we can inject the CO2 in this formation? That's gonna be the task. And please carefully review the lecture note and follow the instruction here. So I didn't provide any details here, but I just provide a hint. So each cells are supposed to accomplish the following the task. So once you finish this one, then you will get the outcome. And again, please, once you finish this task, then please summarize it in less than 2 pages of the PDF. And if you need it, then then you can also include the snapshot of your Python run into the final report. And this one is due on October 24th. So please submit this before the midterm exam that we have on this day. And this is what I prepared for today. And let me know if you have any question. And thank you for listening.